Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our second video lecture, and we want to prove some facts about differentiation and some differentiation formulas. And here's our first definition. It says, given a function f defined on the closed interval from A to B, we assume, or we associate, I should say, a function f prime called the derivative of f whose domain is the set of all points in A to B such that, let's call those points a generic name, x in A to B, such that the limit as t goes to x of phi of t exists. So 2f, we associate this function f prime called the derivative of f, and its domain is the set of all x in A to B such that this limit exists. Okay? Continuing on with this definition, if f prime is defined at x, then we say f of x is differentiable at x if f is defined if f prime is defined at every point in a set E that's a subset of the closed interval from A to B. Then we say f is differentiable on E. And of course, here just in parentheses, let's don't forget f prime of x is equal to the limit as t goes to x of phi of t is equal to the limit as t goes to x of f of t minus f of x all over t minus x. And we're thinking of this f prime of x now as the derivative function. Okay, Let's look at an example. So if f of x is a constant function, then f prime of x equals to 0. Okay? So this is an example, but really it's a fact too. And so let's prove this. Let's let f of x be a constant. Say f of x is equal to b in this domain, where b is an element bar and it's a fixed element bar. Okay? And let's say that's true instead of just saying, any domain, let's say the domain is all a bar. Okay. Okay. Well, we'll let epsilon be greater than 0 be given. I'm sorry. That's one way of doing it. What we're going to do is this. Note, phi of t, in this case, is equal to f of t minus f of x all over t minus x. But that's going to be equal to b minus b over t minus x, which equals to 0. Okay? So, the limit as t goes to x of phi of t, which is going to be equal to the limit as t goes to x of 0, which is equal to 0. And that's true for all x in R. So that says f prime of x is equal to 0. And that's the proof. As another example slash fact, if f of x is equal to x, then f prime of x is equal to 1. See that proof? Okay, so let's let f of x equal to x. Now, f prime of x will be equal to the limit as t goes to x of f of t minus f of x all over t minus x, which is equal to t minus x over t, oh, I forgot one. It's the limit as t goes to x of t minus x over t minus x. T minus x over t minus x is just 1, so this is the limit as t goes to x of 1, and the limit of a constant is the constant, so we just get 1, and that is that proof. Now, we want to make sure that we're defining the derivative on the closed interval. So if f goes from A to B into R, then keep in mind f prime of A can be defined. But what it will be is that the limit as t goes to A from the right of phi of t, and f prime of B, that can be defined as the limit as t goes to B from the left of phi of t, provided these exist. Okay, so that's just something I wanted to take note of. I'm not going to do an example of it. But the next thing I want to list is a fact that we want to prove. And this fact we'll call a theorem. And it says let f be defined on A to B. If f is differentiable at the point x element of A to B, then f is continuous at x. So differentiability implies continuity in this setting. So let's look at the proof. Note, x is a limit point of A to B. If you're a point in A to B, you're a limit point of that set. Now, the limit as t goes to x, so this will be the derivative provided it exists, of f of t minus f of x all over t minus x. Okay? I'm sorry. Let us look just at this. The limit is t goes to x of f of t minus f of x. Look at this. Okay? Now that's equal to the limit as t goes to x of f of t minus f of x all over t minus x times t minus x. And we know this derivative exists. And this, we know that this limit as t goes to x of this quotient function here exists because f prime of x exists, and that's what this is. The limit as t goes to x of t minus x, that's 0. So we have a limit of a product, and since both of these limits of each factor in these products exist, we can break that down as the limit as t goes to x of f of t minus f of x all over t minus x times the limit as t goes to x t minus x, and that's f prime of x times, and this limit is 0. And so that equals to 0. Okay, so since the limit as t goes to x of f of t minus f of x equals to 0, then that implies that the limit as t goes to x of f of t equals to f of x. Now, since x was a limit point of that set, and the limit as t goes to x of f of t is equal to f of x, that implies x is a limit point of a to b, and the limit as t goes to x of f of t equals to f of x, then that implies that f of t is continuous at x. This implication was something we reviewed in video lecture 1. What I'd like to say and show through an example is the converse of the statement we just proved is not true. So what we just said was, if you're differentiable, then you're continuous. However, you can be continuous without being differentiable. And here's an example. If we let f of x be equal to the absolute value of x, then f of x is continuous at 0, but f prime of 0 does not exist. And I will prove that. Proof. We're going to let f of x be equal to the absolute value of x, where we are thinking of f going from R into R, and R is endowed with the usual metric. Of course, what I mean by the usual metric is the distance between these two real numbers is the absolute value of their difference. Okay, we're going to let epsilon be greater than 0 be given. Okay. The first thing we're going to try to do is show continuity. So we need a delta greater than 0 such that the absolute value of x minus the absolute value of 0 is less than epsilon, and that's true for all x element of R such that, or with the absolute value of the absolute value of x, such that the absolute value of x minus 0 is less than delta. So we want this to happen, but if the absolute value of 0 is 0, absolute value of x minus 0 is just absolute value of the absolute value of x. So that's just the absolute value of x. We want that to be less than 0. So we want the absolute value of x minus 0, which is equal to the absolute value of x, to be less than epsilon. So we just let delta be equal to epsilon. Thus, this shows that f of x equaling to the absolute value of x is continuous at 0. Okay. Now we want to work on the non-differentiability at 0. So note, the limit as t goes to 0 of phi of t will be equal to the limit as t goes to 0 of f of t minus the absolute value of 0, or f of 0, I'll write down f of 0, all over t minus 0, which equals to the limit as t goes to 0 of the absolute value of t, f of 0 was 0, so minus 0, all over t, which is the limit as t goes to 0 of the absolute value of t over 0. So that's what we're looking at to be the derivative of our f at 0. Now, what we're set out to do is to show that this does not exist. This limit does not exist. This derivative doesn't exist then. But we're going to do that through contradiction. So let's suppose that it does exist. Suppose this limit does exist. Say this limit equals to some number L. Then, for epsilon equal to 1/2, let's say, there exists a delta greater than 0, such that for all t with 0 less than the absolute value t minus 0 is less than delta, then the absolute value of t over t minus L will be less than epsilon, which is 1/2. Okay? As we had done in the example in lecture 1, if we look at minus delta over 2 and delta over 2, they are numbers such that the absolute value of minus delta over 2, which equals to delta over 2, is less than delta, and delta over 2 inside absolute values is equal to delta over 2, which is less than delta. So for t equal to delta over 2, so these two numbers we're saying are numbers that if you take absolute value of that difference from 0 to that number, it's going to be less than delta. And so this must occur. So when t is equal to delta over 2, we have the absolute value of delta over 2 over delta over 2 minus L will be less than 1/2. Thus, it says 1 minus, because the absolute value of delta over 2 is delta over 2, so this is 1 minus L will be less than 1/2. And that says that minus 1/2 is less than 1 minus L, which is less than 1/2. If I subtract 1 from both sides, that says minus 3/2 is less than minus L, which is less than minus 1/2. So solving for L, what we would get is that 1/2 less than L, which is less than 3 halves. Now for t equal to minus delta over 2, we have absolute value minus delta over 2 over minus delta over 2 minus L is less than 1 half. So this is delta over 2 over minus delta over 2, so that's minus 1 minus L is less than 1 half. That's what we have. And that tells us that minus 1 half is less than minus 1 minus L, which is less than 1 half. Again, we want to solve for L. I add 1 to both sides. That says 1 half is less than minus L, which is less than 3 halves. And so that says that minus 3 halves is less than L, which is less than minus 1 half. Okay. So if you look at this part and this part, that they cannot both happen. These are contradictions. So no such L exists. And that means, so f prime of 0, which was equal to this limit as t goes to x of absolute value of t over t, does not exist. It does not exist. And that is the proof of this example. Okay. Okay. Here is a theorem we'd also like to look at. It says, suppose F and G are defined on A to B and are differentiable at a point x, which is an element of A to B, then f plus g, f times g, and f divided by g are differentiable at x. Moreover, we can say what the formulas are for their derivatives. So f plus g's derivative evaluated at x is f prime of x plus g prime of x. Part B is that if you take the multiplication and look at its derivative at x, that's equal to f prime of x times g of x plus g prime of x times f of x. And finally, part C, you take the quotients derivative evaluated at x. That's going to be equal to g of x times f prime of x minus f of x times g prime of x all over g of x to b squared, okay, to b squared, bottom, and that's provided, of course, g of x is different than 0, so where? And look, this is called the sum rule, the differentiation rule, this is the product rule, and this is the quotient rule. So we'd like to prove these three. Okay. So, prove, we're going to let F and G be defined on A to B, and suppose F and G are differentiable for an X element of A to B. Say at it's an element of A to B. Okay, so part A, we want to show that F plus G prime of X is equal to F prime of X plus G prime of X. Well, here's where we'll do this. Note, F plus G prime of X, if it exists, is equal to the limit as t goes to x, and here it would be phi of t. Well, that's equal to the limit as t goes to x. Now, what is phi of t in this situation? Well, it would be F plus G acting on t minus F plus G acting on x all over t minus x. And then, using the definition of F plus G acting on something, we get limit as t goes to x of F of t minus G of t minus F of x minus G of x all over t minus x, which we can rewrite as the limit as t goes to x of F of t minus F of x over t minus x, and then I'll say minus G of t, and then this will be, let's make this plus, and let's write down G of t now. So it should be, let's see, it should be minus, well, let's make this, let's say a plus for a second. This is going to be minus G of t minus G of x all over t minus x. That's what I've got written down. I've made a mistake here. That's why I'm having trouble. This should be a plus. And so this should be a plus, and then it's G of t minus G of x all over t minus x. That's what we are. Now, both of those limits exist, so the sum of the limit are equal to the limit of the sum. So I'll rewrite this as the limit as t goes to x of F of t minus F of x all over t minus x plus the limit as t goes to x of G of t minus g of x all over t minus x. Which equals to, this is f prime of x plus g prime of x. And so that's what we wanted to show for part A. Part B, it's a little bit more difficult, but not by much. So f times g derivative acting on x is equal to the limit as t goes to x of f times g acting on t minus f times g acting on x all over t minus x. And then using the definition of derivative here, using the definition of multiplication between two functions, that's the limit as t goes to x of f of t times g of t minus f of x times g of x all over t minus x. And what I'm going to do is introduce, add and subtract the same quantity. So we're going to introduce a funny looking zero. Namely, we're going to say that's the limit as t goes to x of f of t times g of t minus f of t times g of x plus f of t times g of x minus f of x times g of x all over t minus x. Okay? So I've just inserted one thing in terms of the subtraction and its addition. So that's equal to the limit as t goes to x. All right, now f of t times g of t minus, so I'll break this up into f of t g of x, so forgive me, I'll go a little slow here, over this t minus x plus the limit as t goes to x of f of t g of x times g of x minus f of x g of x all over t minus x. Now here, there's something in common. There's an f of t. So I'll pull that out. So the limit as t goes to x of f of t, and then times something, but I'm going to rewrite that as the limit of the second part, t goes to x, of g of t, so I'm pulling out, the f of t, so g of t minus g of x, and this is all of the t minus x, plus, here, this is the limit as t goes to x, and what can be pulled out here is a g of x, and then times the limit as t goes to x of f of t minus f of x all over t minus x. Now, because of continuity and x being defined, or f being defined on a to b closed interval, and x being in there, x is a limit point of that closed interval. So because of f being differentiable, that says f is continuous at x, and so that the limit as t goes to x of f of t is nothing more than f of x. Here, this is the derivative of g evaluated x, plus this is the limit of a constant, so it's just g of x, which is the constant itself, and what follows is nothing more than the derivative of f at x, and that's what we were trying to show for part B, and that's just the formula of the product rule. Lastly, we want to do the quotient rule. So for part C, when we look at f over g's derivative That's equal to the limit as t goes to x of f over g evaluated at t minus f over g evaluated at x all over t minus x. And by definition of quotients of functions, this is equal to the limit as t goes to x of f of t over g of t minus f of x over g of x all over t minus x, which we can rewrite getting the common denominator as the limit as t goes to x. This will be f of common denominator is f of t, g of t times g of x. So this will be f of t times g of x. You know what? Let me write it down here. It's equal to the limit as t goes to x of f of t times g of x minus f of x times g of t. All over the bottom will be g of t times g of x, and then really times t minus x. Okay, and now we can rewrite this as the limit as t goes to x of 1 over g of t times g of x, and then times f of t times g of x minus f of x times g of t all over t minus x. Okay? Now, that can be rewritten as the limit as t goes to x of 1 over equals g of t times g of x times the limit as t goes to x, and I'm going to change what we have there. I'm going to rewrite it as f of t g of x. I'm going to introduce a funny looking 0 minus g of x times f of x plus g of x times f of x. And then we had the minus f of x g of t there. Okay? That was already there. All right? That's going to be equal to, well, because of the derivative of g existing at x, the limit as t goes to x of g of t is g of x, so this is equal to 1 over g of x, and the limit as t goes to x of g of x, that's the limit of a constant, that's g of x, here, times, oops, I forgot something. Over here it should say t minus x. So we'll break this up into the limit as t goes to x, f of t, g of x, minus g of x, f of x, all over t minus x, and then plus the limit as t goes to x of g of x, f of x, minus f of x, g of t, all over t minus x. This is 1 over g of x to be squared, which is good because that's what the bottom of 1 again is. And then here we can pull out, I believe, a g of x is the limit as t goes to x of g of x times the limit as t goes to x. What I'll be left with is f of t minus f of x all over t minus x. Plus, what I'm going to pull out here is a minus f of x. So let's make this minus f of x, well, I should put a limit out front of it. Limit as t goes to x. Let's make it plus or minus f of x in that form. There's a minus there. And then times the limit as t goes to x. What I'd be left with if I took out a minus. And this would just be g of t here, and this would be a minus g of x all over t minus x. We do that so that we can recognize that as the derivative of g evaluated at x. So this is 1 over g of x to b squared. Here, the limit as t goes to x of a constant is g of x. Here, this is f prime of x plus this is minus f of x, and then that's g prime of x, which is exactly what we wanted because it's g of x times f prime of x minus f of x times g prime of x all over g of x to b squared. And that ends that proof. All right. What I want to do lastly is write up the chain rule, and I'm just going to state it, and then we'll prove it next time. But first, let me make this comment. What we have done so far, so let me make this comment first, and then I'll write up the chain. Since we have proven that the derivative of a constant is 0, and the derivative of f of x equal to x is 1, then the previous theorem gives that all polynomial functions and rational functions are differentiable except for where the denominators, that's on rational functions, are 0. Matter of fact, I said something about the chain rule. Here's what I was going to do next. But let's just save that for next time. So I'll state and prove that next time. That's enough for today. Thank you very much.